So I'm going to tell you a bit about the stuff that James Webb found on the atmospheres of exoplanets. So, James Webb in a nutshell. It doesn't fit in a nutshell because it's huge, right? It's 6 meters wide, the mirror, and it has several instruments on board. It took over 30 years to build, and it is the largest and most powerful space telescope we currently have. It was launched in December 21, and now we have a lot of data from it. And what I think many of you know what James Webb is, right? Because it has been all over the news. What you maybe not know is that actually the Netherlands had played a big part in one of the crucial instruments that is on board the James Webb Space Telescope. It's not all NASA in the US. Actually, this instrument was built in the Netherlands, and it was the first instrument that was shipped to the telescope back in 2008. We shipped it to the UK, and then in 2012 they actually shipped it to Webb to be integrated in the telescope, and then in 2021, 9 years later, it was launched. Right, so I think that it's a great achievement, and this is also why we in the Netherlands are actually part of the guaranteed time of James Webb, which gives us access to amazing data and some amazing results, of which I will not present everything yet, because we are still analyzing a lot of data. It's just a treasure hunt that is still... so, yeah. It was launched in actually Christmas 2021, and here you see an image of the presentation of the first images. And actually, I was so happy that it didn't launch it 2 years earlier, because just imagine who would have been sitting here, and I think the entire scientific community just dodged the bullet there. So that was good. And then, of course, the first images came out, right? So this, and I was looking at this at night, and I thought, okay, this is boring, right? This is just galaxies and stars and stuff like that. And then you have this image, right, which is also boring. It's just dust and gas, and I don't know what. And then this image came up, right? Which is the most amazing thing. So I was, of course, you can see from the images I now showed, you all see that this is the most amazing one. This is actually the atmosphere of an alien world, right? So this is the atmosphere of a planet around another star. And what we can see is actually it has water in it. That's what we're going to see. We can see a lot of other things as well, but the first thing you can see is there's water in it. So how can you see that? So let me back up a bit. How was this spectrum, how was this data taken? So what we do when we look at exoplanets, we actually look at what happens when an exoplanet goes in front of the star, right? Because when it goes in front of the star becomes a bit dimmer. Right? That's how we find exoplanets. Right? And if the planet is bigger, the dip is bigger, so we know it's a bigger planet. It's all very nice. Right? That's simple. Then we know how big the planet is. So that's cool. We know that it's a planet, we know how big it is. But actually the fun thing starts when you realize that this planet has an atmosphere. And part of the light of that star filters through the atmosphere. And atmospheres have the nice thing that they are not as transparent at every wavelength as other wavelengths. And so what you can do is, here you have another planet, and you see the size of the planet actually changes as a function of wavelength because of the different molecules that are in the atmosphere. And the different molecules absorb light in a different way, in a different amount, and that's why in the wavelengths where the atmosphere is actually transparent, the planet looks smaller than in the wavelengths where the atmosphere is not transparent. So by measuring the size in different wavelengths, we can actually learn something about where the atmosphere is transparent, and that tells us which molecules are in the atmosphere. So that is the method that is called transit spectroscopy, and that's why this image from James Webb, the spectrum that we had, was so exciting. Now, this is the first real big science result that we had. And here again I show a spectrum. So I'm going to explain it. And here on the x-axis you see the wavelength of light. So that's just the color of light. And then here you see the amount of light that is blocked by the planet. And you see the white data points. This is not the same at every wavelength. And before James Webb, you have to realize, before James Webb we had Hubble. Hubble is a great telescope. Hubble had access to this part of the spectrum, this tiny bit. And that is actually the only thing that we could learn from Hubble is if there is water in the atmosphere or if there is not water in the atmosphere. These are the two things that we could learn, right? Is there water, is there not water? You can even argue that it's one. So, but now with Webb, you see here we can see things like carbon monoxide, carbon dioxide. Here we have sulfur dioxide. Sulfur dioxide is the gas that is released if you light a match, right? It's burning brimstone. It's like hell. This planet is like hell. And carbon dioxide, right, which is a greenhouse gas. And now we have this spectrum. This is just one spectrum of a planet, and we can learn about, okay, what kind of gases are in the atmosphere. Things like sulfur dioxide, we didn't expect that. We didn't expect to see that because it's not expected to form under normal chemical circumstances in an atmosphere like this. This is really an effect of the photochemistry. So this is an interaction of the planet with its host star that is creating this burning brimstone. So this is the first result, and it was published in Nature because of CO2, and CO2 of course is a hot topic in atmospheres because we have too much of it. But what I find very interesting is if you look at our solar system, right? So this is our solar system. It just has 8 planets, 9 if you count Pluto still. So people do. And all these planets, they have different types of atmospheres. They have different types of cloud structures forming, right? If you look at Mercury, it doesn't have an atmosphere at all. If you look at Venus, it has a very, very thick atmosphere, 100 times as thick as the Earth, and it's completely made of CO2. Then you look at the Earth. Well, we know what the Earth is made of, right? It's a nice atmosphere. Mars has a tiny, tiny atmosphere, also mostly made of CO2. And then you have Jupiter, which is 99% atmosphere in its whole. And Saturn, which is different, and Uranus and Neptune. And actually, Jupiter has clouds made of ammonia, right? We have clouds made of water. Venus has clouds made of sulfuric acid. All these different types of atmospheres, all these different types of clouds. And one of the things that we were expecting, actually, is sand clouds. And, okay, you can ask yourself, sand clouds, what are these? So this is the Earth's cloud system, right? So how does that work? Basically you have water on the surface. And that water evaporates, right? If you just heat it up a bit, some of the water comes into the atmosphere as vapor, and in the top part of the atmosphere it condenses into clouds because it's cooler, and then it rains down again. And then the whole cycle starts again. Now, you can imagine if you increase the temperature of an atmosphere, you can do the same thing, but then not with water, but with rocks. And actually this has been found now. In one atmosphere, there's a hint that we see these types of sand clouds, rock clouds, quartz clouds, crystal clouds, whatever you want to call them. And actually they are basically it's the very same principle. You have rain there, and the rain is not water, the rain is simply rock, the rain is sand. And we also have these kind of things where the rain is just iron droplets, right? So imagine waking up on an atmosphere like on a planet like that, where you have just a slight drizzle of sand and the smell of burning brimstone in the morning. Then another thing that you can actually do with James Webb, which is what we also did, is you can measure the temperature of a planet. And how do you do that? So I've now been talking about what happens when the planet goes in front of the star, right? And then a bit of light filters through the atmosphere, and you can actually measure the composition of the atmosphere that way. The other end, of course, is when the planet goes behind the star. And when the planet goes behind the star, just before it goes behind the star, you see the very, very hot day side of the planet, right? You just look directly at straight midday of the planet. And then when you take the difference between when the planet is just beside the star and when it's just behind the star, the difference of these two spectra that you take is just the spectrum of the planet, right? So in that way, we can measure a tiny, tiny signal that you actually get from the planet just by taking this difference. And in this way, we can measure the temperature of the planet. So here you see the temperature, right? This is then the temperature of the Earth, right? Which is around, well, 300 Kelvin or so. It's quite nice. 300 Kelvin is 20 degrees or so, 20 degrees Celsius. This is this is actually where was Mercury? Mercury is here, very, very hot. And then we measured the TRAPPIST-1b. TRAPPIST-1b is a planet the size of the Earth. It orbits a star, TRAPPIST-1, and it orbits it as a distance which is approximately the temperature of Venus. Should be the temperature of Venus, right? So we expect first, okay, very big CO2 atmosphere, right? That would be our first order approximation. But then you make actually a model for TRAPPIST-1b, and you say, okay, if it has such a big atmosphere, what would its temperature be? You say, well, around 400 Kelvin, right? And now we measured, and the measured temperature is actually above 500 Kelvin. So it's 100 degrees warmer than we expected. And the only way we can do this is completely stripping it from the atmosphere. Well, the only way, that's not entirely true. We're learning. There might be other solutions. Stay tuned. We're not there yet. But this is the solution that was published in Nature, where they say this planet doesn't have an atmosphere. We're collecting more and more data. We're learning more and more about these atmospheres and about these planets. So maybe we have found actually a way around it, but we still don't know. It's all also to us, it's completely new, so we're still figuring this out. But just by measuring the temperature of the planet, we can already say a lot about the atmosphere. So then, this one, K2-18b, we are not very nice with making names up for these planets, but this was something that was in the news, and maybe you've seen it. It was very recent, a few weeks ago, where there was a whole hype about what they found was dimetal sulfide. So dimetal sulfide, what's that? So that's a sulfur thing, so again, sulfur species, but this one can actually chemically only be made by plankton. Life. So, of course, media hype, life. Actually, if you read the paper, they say, well, yeah, could be there, could not be there. We don't know. It could be something else. It could be this, could be that. And if you look at the measurements, right? So these white dots, they are the measurements. They go up and down, right? That's nice. And then here, there is supposed to be something which is dimetal sulfide. And yes, statistically speaking, could be. But reality, I think the scientific consensus now is this evidence is really, really not there. What is very interesting in this atmosphere, there is actually methane detected, and there's carbon dioxide. There is the hypothesis for this planet to be completely covered by an ocean. So in that sense, finding a planet that is completely covered by an ocean, where there is a hint of dimetal sulfide, is of course exciting in itself. But this spectrum doesn't give that proof. It does say, okay, well, there is a proof of concept. Maybe if we look long enough at this thing, we find something. Maybe if we look long enough at planets like this, we'll find something. But just to be sure, we haven't yet. So, what is our final aim? Our final aim is to have a weather forecast for all these planets, right? If we look long enough, and I hope I convinced you of that, what we can actually see in these planets is the composition of their atmosphere. We can see the composition of their clouds, right? We can see basically maybe differences between the morning and the evening on these planets. We can see the day side of the planets. And then we can try to start, and this is actually a real thing where we already have this kind of information. We can measure the temperature of the morning, which is, in this planet, 1500 degrees Celsius. It's not very nice. It has a wind speed of 2004, right? Which is not something that you want to have here on Earth. And then in the night, we know that there are rains of iron, right? So there are clouds made of iron, and it rains iron droplets. This is another example. This is a super Earth. This is a planet which is a few times the size of the Earth. It's basically, the surface is completely molten, and the atmosphere is just made by outgassing of that molten rock. So also there, when you form clouds in the atmosphere, you form rock clouds, and it rains down again. You have this entire cycle that I explained that you have on Earth with water. Here you have just with molten rock. And then in hot Jupiters, what I also showed you is we have these sand clouds and we have these sand rains. And then you have the smell of burning brimstone in the morning. You wake up like you feel like you're in hell. If you could ever wake up on a planet like this, because they're way too big and way too hot and way too, so that you wouldn't survive anyway. But I think this is where we're going to, right? This is where we're heading. And unfortunately, the whole data analysis and whole interpretation of all these amazing spectra that come from James Webb is hugely complicated, and more complicated than we've ever thought. And I think there is really a lot of data still on the computers of everybody who ever took an observation of it with this, and they're trying to make sense of it. So I think if we're a bit patient, there's really a lot more of these kind of interesting results to come. So this is actually what I want to end with. You can read it, right? It's weird to think that all these planets are out there. They all have amazing atmospheres. They all have amazing cloud structures. And now with James Webb, we can actually see a glimpse of what they are. And the future, I think that is what Peter is going to tell you about after the intermission. But this is what I wanted to say.
Yeah, I was wondering, I think it was 76B, you had wind speeds. Is that from Doppler shift or modeling, or where does it come from?
Yeah, good question. That comes from Doppler shifts, actually, indeed. So actually, this is not measured by James Webb. This is measured with the ground-based telescope, where you have very high resolution spectra, and there you can measure the Doppler widths of the lines, and these tell you the wind speeds. Yeah. Thanks. Yeah. Derek back.
Can you please explain the weird naming system?
Yes, I can. Yes. Well, not entirely, but a bit. So actually, mostly it's the telescope that discovered the planet, and then just a number, and then a B, because so for example, Corot is the telescope that discovered this one. It's the 7th planet discovered by Corot, and actually Corot 7 is the star, and Corot 7b is the first planet discovered around it. So in TRAPPIST-1 is the star. TRAPPIST is actually the instrument that discovered the star, or discovered the planets, and then you have B, C, D, E, and F that are the planets going from inside to outside. It's very boring, but that's what it is. And actually K2 is the Kepler 2 mission, so that's the second version of the Kepler catalog. Yes.
You talk about TRAPPIST-B, but I think I have also seen data about TRAPPIST-C.
Yes.
How is the information on the other planets?
Yes, so, yeah, very nice question. Indeed, TRAPPIST-1c, I decided to leave it out because of time. The nice thing about TRAPPIST-1c is actually there we did exactly the same measurement, right? But we found that it is slightly colder than TRAPPIST-1b, if you would put it at the same distance, right? It's of course it's a bit further out. And that means that actually TRAPPIST-1c is consistent with a CO2, a thin CO2 atmosphere. And the reason that is that an atmosphere has, of course, has different temperatures. If you go up in the atmosphere, it has different temperatures. And usually the warmest is the surface, and then you go up and it becomes colder. So actually TRAPPIST-1c we measure somewhere higher up in the atmosphere because you have CO2, so you don't see all the way through the surface, and then you measure a slightly lower temperature. So actually that is a measurement which says there must be something. There must be something like a Martian atmosphere or so. Yeah. And the others actually I haven't seen very much data on yet. It must be on somebody's computer, but and actually for TRAPPIST-1b we also have more data, but I cannot tell you about it yet because I'm not allowed to. Sorry. Yes.
You told us that the James Webb Telescope was the biggest space telescope. How many do we have?
Yeah, really a lot. So here, actually, here you can already see a selection of them. Yeah, so we have many telescopes. We have dedicated telescopes that have basically served just one purpose. Things like Gaia, for example, that we saw earlier, is a telescope that really is a surveying mission, right? So it is designed with a very specific purpose in mind, and it just does just that one thing. But a telescope like James Webb is a more general, just takes pictures and spectra, and you can apply for time on it. So we have different types of telescopes in space. How many?
A lot.
A lot, yes, exactly. Yeah. Yes.
Can you elaborate on the complexity of analysis of the data? Is it mostly because of the raw signal, or the lack of models, or the number of parameters?
All three. But so the thing is, what we do with the transit spectrum, you have to realize. I can show you the transit spectrum again, right? So, for example, this one. What you see, the amount of light that is blocked is around 0.3%. Okay, that's something we can measure. That's a small dip in the total light, right? It's 0.3%. That's of course that's not much. But then you see that the amplitude of the spectral features that actually tell you the composition of the planet, it goes from 0.29 to 0.30%, right? So that's 0.01%. That is just 1 in 10,000. And that is the signal we're interested in. And that just makes it hugely complex, because actually James Webb was not designed to do this. Because when James Webb was designed, we didn't know that this technique would work, because we didn't know so much exoplanets. Transit spectroscopy was just something very new and weird. And James Webb was simply not designed to do this. So now we're struggling with things like very technical things like detector nonlinearity, right? So if the flux goes twice as much, do we actually measure exactly twice as much flux, or do we measure 2.00001 times as much flux, which makes a huge difference for the spectrum. And all these kind of nitty-gritty details, they all matter. So we work together with people that know all about the instrument, that have actually helped design the instrument, that know exactly how all the technology works to gather out these tiny signals. So that's one hurdle. The other is that we find things like in this spectrum I showed, right? We find sulfur dioxide. We didn't expect that. So then you can just say, well, that's sulfur dioxide, but it's a tiny signal. You didn't expect it. Can you trust it? So you first have to come up with a theoretical argumentation on why it should be there. So you have to further develop your models. So that's also hugely complicated. So it's all these things. We see things that we didn't expect, and we need to figure these out in very tiny signals. Are they real? Are they not real? It takes really just publishing one of these spectra takes a year easily with many people. Yeah. Thank you. Yes.
Yeah, a bit related to last question. So, do you have a confidence level or probability? Because you can't be sure. So, when do you decide that you have detected something?
Yeah, that's a very good question. And so what we do typically is we make a model of the atmosphere, and then to decide, for example, something like this, sulfur dioxide. Is it there or is it not there? We make a model to the spectrum and we fit it, which means we compute 1 million different compositions of the atmosphere, and we just see, do they fit the data or not? And then we do the same procedure, but we don't include SO2, and we see, is the fit to the data significantly worse, and then you can do basically just the statistics to see, does that work? Now, so that is basically the kind of easy answer, right? This is what we do with the statistics. And then what happens is you do that, and you find, my model gets significantly better if I include dimetal sulfide. This is what you then find. Right? You find that. And then you have to ask yourself the question, is this significance real, or is this just an unlucky draw of the data, right? Of the noise. And in this paper, they make a very solid kind of argumentation around that yeah, no, probably not real because but of course journalists don't care about statistics, right? So they just pick it up. And it's the formal statistics that you have to do, and then you actually have to look at, okay, do I actually see it in my data, or is it just statistics? This is a very tricky question. Yeah.
Yeah. I suppose that we also did this with our own planets, right? Because we probed their atmosphere. So did we run the same kind of observations with our own planets, given the probed atmosphere, and make a comparison between what we probed and what we then observed with our own planets?
Yeah. So actually, our analysis tools that we use, they originate in studies from the solar system, studies from the Earth. Actually, the tools are very similar. And the very big difference is that here we look at an integrated signal of a planet, and you see the noise level is huge, right? The signal to noise is just very poor. If you look at the Earth, if you have an Earth orbiting satellite, it just takes a snapshot of the Earth at each location, and it has so much light that the data is just completely exquisite, right? It's not comparable at all to what we have here. So the statistics that you do is of a whole different level. And that goes actually for all the planets in the solar system. Usually we have so much better data from the planets in our solar system. And even there, actually, maybe you remember, it was a few years ago when they found phosphine in Venus, right? It was the same kind of problem as you have here. They found phosphine in Venus, statistically it was sound, and it was proven afterwards to be just basically a bad calibration of the instrument. These things happen also in the solar system, unfortunately.
Thanks.
We have time for one more question. In the back.
I have a question about the TRAPPIST-1b planet. When observed, it had a higher temperature than was predicted by the model. And this could be explained by removing the atmosphere. I usually think about atmosphere as kind of this blanket around the planet. So how could it increase the temperature?
Yeah, that's an excellent question, because so the reason behind this is actually simple. If you have a rock and you illuminate it from one side, it gets warm on one side and it stays cold at the other side. And the thing is that a planet is always in energy balance with its star, right? So if you then put an atmosphere around it, what happens is what that atmosphere does, it actually transfers some of the heat from the day side to the night side, which means the night side heats up, but the day side cools down. So yes, it's a blanket, but the blanket actually happens, and this is what happens to Venus. The surface of Venus is extremely hot, but the atmosphere we see, the visible atmosphere that we probe with measurements like this, is actually pretty cold. And if you would remove the entire atmosphere from Venus, then what we would see is a surface which is colder than what it now is, but actually hotter than the atmosphere that we see now. So it's a complicated thing. It's basically, the simple answer is energy balance, right? You just remove heat from the day side and move it to the night side by the atmosphere.
Okay, so let's thank Michiel again. So now we're going to have a very brief intermission, 5 or so minutes, where you can get drinks, and then at the end of that 5 minutes, we're going to reconvene and do our quizzes.